Hello again, class. We're going to start the second part of our algebra review now. We're going to start with the difference quotient, which is a concept from algebra, very similar to calculating slope. As a little sidebar, remember that the formula for slope is y2 minus y1 over x2 minus x1, because you call the coordinate points in particular in this x1, y1, and x2, y2. The difference quotient really represents the slope between 2 points, but instead of referring to them as x and y, we'll use function notation. So our first point will be x comma f of x, and our second point is similar to the first point, but it's moved a certain distance to the right, and we call that distance h, so it's now x plus h and f of x plus h. But if you just plug them in the same way that you do the slope formula, then you get the simplified version of the difference quotient, which is f of x plus h minus f of x over h. This is going to have massive implications in calculus, especially for helping us transition to understanding how calculus works. It's like the intermediate step. So let's just practice applying this, because you will be applying it many, many times this semester. So we're given f of x. What we really need is f of x plus h. So f of x plus h is replacing x, all x's, with an x plus h. So in this case, the 10 minus x becomes 10 minus x plus h. And we can't forget to distribute. This is 10 minus x minus h. And so what we're going to do is, according to the formula, take our three pieces of information. One is f of x, which was given. One is just h. And the other one is the f of x plus h that we just found. And we're going to subtract 10 minus x minus h minus our original function, 10 minus x, and divide it by h. Now don't forget to distribute the negative. This is 10 minus x minus h minus 10 plus x all over h. When you do this right, generally, all of your terms that don't have h's should cancel. Now if we look at this, 10 minus 10 cancels, negative x plus x cancels. The only things that will actually survive the simplification process is negative h over h. However, we know if you take something negative and divide it by the same value that's positive, those two cancel and it simplifies to negative 1. Now, again, we said this represents slope. We don't really need to do this for linear equations. As you can see from above, we could look at this function and already know what the slope of this line was, because the coefficient for x is negative 1, but it's still a good practice. I'm going to leave the second one for you to do, where you can't use that obvious knowledge of what the slope is, and be very careful. Remember, when you're plugging in f of x plus h, every x is replaced with x plus h, which means you will have to use the distributive property, particularly for this x squared. Now, another thing I would like to look at is inequalities, primarily to remind us how we deal with inequalities, or deal with knowing if something is positive or negative. In quadratic inequalities, it's very similar to solving the quadratic equations from previously, but we have to have like an additional step at the end. So it involves that sign table that you've probably seen before, possibly here, maybe even in pre-cal. So find the intervals of the domain that satisfy the following conditions, where x squared minus x minus 12 is less than 0. Okay, so the first thing we need to find or reason through is that in order for a number to be less than 0, it's got to cross 0 at some point. So, and the only places to cross from positive to negative are at the zeros specifically. So we need to find the zeros of this particular quadratic. So we will set it equal to 0 to find the zeros. And this will require factoring. So this factors into x minus 4 and x plus 3. And I'm going to put still where it's less than 0. Now, what two values produce our zeros? That's when x is 4 and x is negative 3. And we will put those in a sign chart to represent the idea here that we know what this shape is. It's a parabola, And parabolas are either above 0, below 0, or at 0, just like anything else, as long as they're defined at that point. So we just need one value in each of these little ranges to represent all of the values in that range. So we're going to pick a nice number to plug in, less than -3, one between -3 and 4, and one greater than 4. So I'm going to pick -4, 0, and 5. And remember, we don't actually care what the value is, we just care if it's positive or negative. So I like to plug into the factored version in this case. -4 minus 4 is a negative. -4 plus 3 is a negative. A negative times negative is positive. Plugging in 0. 0 minus 4 is negative. 0 plus 3 is positive. Negative times positive is negative. And if we plug in 5, 5 minus 4 is positive. 5 plus 3 is positive. Positive times positive is positive. So what this tells us is every value in this range up to -3 is positive. Every value plugged in between -3 and 4 is negative, and every value from 4 on up is positive. Now, particularly our inequalities wanting to find all of the areas here where this function has negative outputs. So we don't really care about these two because they have positive outputs, but we do want this one, and it produces the interval. Now the interval starts at -3 and ends at 4. Because there's no equal to sign, we just leave it at that. We use parentheses. If there was an equal to sign, we would use brackets instead. Now, in addition to doing this for quadratics, we can also do this for rationals, when we have to ask ourselves, where can the sign change in a rational? The signs change in rationals when the numerator changes sign or when the denominator changes sign. But just like with the quadratics, we really need this to be something greater than, less than, greater than or equal to, less than or equal to 0. So if it's not already that way, you need to get it that way yourself. Furthermore, you need all of the things on the left side in one fraction if you're going to get 0 on the right side. Luckily for us, 1 is already like that. So once you have it set equal to 0 or less than 0 or greater than 0, you set the numerator and the denominator equal to 0. So x minus 5 equals 0 and x plus 4 equals 0. And that produces values of x equals 5 and x equals -4. These are our two places where the function could change signs. In particular for x minus 5, that is a 0. Where x plus 4, though, because it comes from the denominator, that's actually at an asymptote. But at asymptotes, you can change signs from positive to negative. So similarly to what we did with the quadratics, we will organize these, -4 on the left, 5 on the right, picking nice values to plug in. I'm going to go with -5, 0, and 6 in this case. And again, we don't care what the sign is, but we're looking at this thing, and we're going to see positive or negative. So plugging in -5, -5 minus 5, negative, divided by -5 plus 4, which is negative. Negative divided by negative is positive. Plugging in 0, we have a 0 minus 5, negative, 0 plus 4, positive. Negative divided by positive is negative. Plugging in 6, 6 minus 5 positive, 6 plus 4 positive, positive divided by positive is positive. And again, in this case, which numbers are we looking for? The ones that are negative. So not these other two regions. Now, what I had said in the quadratics is that if there was an equal to sign in the inequality, you would use brackets. But remember, in rationals, this function is not defined, or this expression is not defined at -4, because when you plug in -4, you're dividing by 0. So if a value comes from the denominator, you never give it a bracket, you only give it a parentheses. So -4 only gets a parentheses for this interval, but 5, because it comes from the numerator, will get a bracket. And I will leave the other two on this page for you to do, and we will continue these notes in the next video.